We saw that the issues, some of the example issues with the plane stress state is what we listed out here. One is in terms of the structural boundary conditions being violated. The other is in terms of the compatibility equations being violated. And thirdly, delamination cannot be even predicted or modeled. So there's no room for inclusion of that possibility, which we know is quite a distinct possibility in reality. So all of those are issues. So that's why these questions typically become important. Is it necessary? Yes, if you are looking at an overly simplified model, so you want to kind of get some rough cut results analysis, so then yes, you can do that. But is it relevant? In most cases it is not. But still you can use that to get to a first cut result, and then probably refine your results and try to get improvised results when necessary. So that's why you need to take a call, but more often than not, especially in aerospace engineering problems and especially with composites, you would see that this is not a good assumption to make, but that's what most books will make, and that's something that probably we will utilize in our some of the things that we do beyond this in the course. But it's good to be aware of the issues involved with it. Yeah. Then yeah, I think that pretty much covers it. Also, the useful thing is that in terms of making it very simple, because already we saw when we went from 9 stresses to 6 stresses how simple it became. Now with these 3 gone, you're just dealing with just 3 stresses now. So your overall what we call as the constitutive law, the stress strain relationship, just becomes now your sigma 1 1, sigma 2 2 and tau 1 2 is all that you're left with. And this is related to the corresponding strains gamma 1 1, gamma 2 2 and 2 gamma 1 2, which are the in-plane strains. And you would have corresponding to this, you would have what is called as typically the notation that is used is Q11, Q22, Q12 and Q66. Anybody tell me why I'm using Q6 as a subscript there, not a 3? Can you guess why I use 6 over there instead of 3, even though it's a 3 by 3 matrix? Yeah, exactly. So what went off is the 3rd, 4th and 5th. What remains is the 6th, and to keep that in mind, this is kind of a standard notation. Most books will typically use this. And this is in the principal material directions. That is, if 1 is along the fiber direction and 2 is along the transverse that is perpendicular to fiber direction, then these 2 will be zeros here in this matrix. What would otherwise be 1 6 and 2 6 terms, right? This should have been Q16 and Q26, but just like in the original matrix itself, once we had made the orthotropy assumption, we had seen that we could put many of those couplings except the Poisson couplings to all be 0. So the same reason holds that this is a coupling between shear and the normal, and therefore those two need to go to 0. But if that is okay as far as the top layer here and the bottommost layer over here in this laminate are concerned, but any in between layer where the angle is also in between 0 and 90 degrees, you would see that you will have non-zero Q bar 16 and Q bar 26. In that case, we will be putting bars over all of these to kind of distinguish. So this is something that is valid in what we call as the principal material directions. So where 1 is same as L and 2 is same as T, and therefore we are using this over here, and that, remember, is an LT over here. So this is essentially a coupling between LT and LT, that is what we are talking of, tau 1 2 with gamma 1 2, right? So that's essentially what we are looking at. So this particular fact that these two are zeros, there's no coupling between shear and normal, is valid only in the principal material direction. So as I said, example cases as the topmost and bottommost plies in this particular way in which the laminate is designed. Otherwise, you would have the same thing. You would instead be putting in a different structural coordinate system. So in non-principal material directions, in other words, what we call a structural direction, because for example in the actual structure you might want to put your x1 along the span of the wing, x2 along the chord of the wing, for example. So in which case you would have it very different from what the fiber directions are in each layer, or even in this simple case for the middle two layers you would have structural directions, because I might want to put my structural axis along the length, the breadth and the height of this structure, and that may or may not coincide with the fiber directions being perpendicular and or parallel in all the layers. So it will be in some layers perhaps. So when you have that, then you have what we call as it's instead of the x1, x2, x3 system, which is what we used here, where of course your 1 was the longitudinal and 2 and 3 were the transverse directions. So just to distinguish these two, we had used T and T prime, but the T prime is no longer of interest because we are looking at everything within the plane. In other words, we are shrinking the whole surface, the plate, into a surface. So that's what we have. But now we can have a new coordinate system, the structural directions, which we can call as let's say x1 bar, x2 bar, x3 bar, which are oriented at a certain angle with respect to the original x1, x2, x3 system. So then you have these barred quantities. Typically you would have x3 bar and x3 one and the same. It's just that the rotation is within the plane. So you see that because the fibers are all still within the plane, even in the second and third, but it's just that it is oriented no longer parallel to the length and or breadth. So therefore it's usually your x3 bar will be x3, whereas x1 bar and x2 bar will be different from x1 and x2 in terms of the cosine and sine of the angle of the fiber orientation, right? So you can of course write it in terms of cos theta, sine theta, minus sine theta, cos theta matrix, multiplying your x1 bar, x2 bar to get to your x1, x2. So that's good as far as vectors are concerned, but this is a second order tensor, so it typically will involve cosine squareds and sine squareds, and when you're going from q to q bar, that will involve cosine power 4 and sine power 4, because both stress and strain are second order tensors. They will involve cosine squareds and sine squareds, whereas your q matrix will involve cosine power 4s and sine power 4s, but essentially this is what we end up with. So in general, your q bar 16 and q bar 26 may not be zeros. So here again, of course, your strains also will be in your new x1 bar, x2 bar system. So we will call these also as gamma 11, gamma 22, and 2 gamma 12 with the bars on top, right? So that's the final result that we have after putting together all of these 7 assumptions. In the second half of the previous class in the morning session, we were talking about plane stress alone separately, but now we are integrating all of these 6 to now talk about the end result of how simple things become. Simplest case, of course, being for 0 degree and 90 degree fibers, but even for any other degree we can actually get this, and your Q11 bar, all of these 6 quantities over here will be related to just these 4 quantities over here. In other words, you have only 4 independent variables now instead of 5 that you had in the 3D material. Now you have 1 lesser, you just have 4 over here. Because you're not interested in the third direction, the thickness direction. So one of them drops off, and you only have in terms of EL, ET, nu LT, and GLT. So you don't have that other additional thing of either GTT prime or nu TT prime we were talking about. That is no longer needed in this model. So because that drops from 5, we have come down to 4 independent coefficients, and to calculate this, I need those 4 plus the theta, the angle which is going to differentiate your x1 bar x with your x1, x2 system. That angle is the fiber orientation angle in any given layer. Okay. So once you have the fiber orientation angle, for example, in this case, top layer is 90, bottom layer is 0, the layers in between are plus or minus 45 degrees. So then you know the value of theta, you'll substitute the value of theta, you'll involve cosine power 4, sine power 4 terms, or cos cube sine, cos squared, sine squared, or cos sine cube, etc. kinds of terms, coefficients will be there, which will be multiplying an algebraic sum of these, weightage being the cosines and sines all the way up to power 4. So it's very easy to see that for vectors you will involve cos theta and sin theta linearly. For stresses and strains which are second order tensors, you will have cos squared, sin squared, and cos into sine. Whereas for this being a fourth order tensor, you will involve cos power c power 4, s power 4 terms. You will have c cube s terms, and c s cube terms, and c squared s squared terms, which will be the coefficients which will be multiplying a sum of these quantities in order to arrive at these quantities. So it's beyond the scope of this particular course for you to kind of get into that, but just to have a flavor of what it actually is. So that's your plane stress state. Any questions on this plane stress state? Okay. This next assumption that we make, have any of you heard of the Euler-Bernoulli beam theory or a simple engineering beam theory? No?
It sounds familiar, but I forget what it is.
Okay. No problem, because we will talk about it in a little more detail later on. But even before we get there, even when you have beams like, let's say, the spar or a stringer, they are actually made out of, let's say, an I section beam or a T section beam, etc. So each part of that I section beam, let's say the flange, the spar, the web, and the bottom flange, each of them is like a plate. So you can go from a 3D model to a plate model, and then from a plate model to a beam model. So remember that in reality everything is 3D, and you know that plate or shell is 2D, because one dimension is very small compared to the other two. If one dimension is very large compared to the other two, you end up with 1D model, which we call as beam, and which is a generalized term we will use, that is the current contemporary style, where we say beam is not just about bending, which is what traditionally it used to be, but beam includes shafts. So it includes shafts which are primarily undergoing torsion. It includes columns which are undergoing compression primarily. It includes rods which are primarily undergoing axial, or rods sometimes are also called as bars, axial bars. So all of these are kind of included in that. In fact, we can go even a step beyond and say we can include frames, because frames are piecewise beams which are joined to each other in some way. You can include even trusses. So in these case, elements of frame elements. It's not the entire frame, the truss element is what we are talking about. So all of those are essentially structures in which one dimension is very large compared to the other. We call that dimension as length. In the case of the plate or the shell, one dimension is very small compared to the other two, which we call, that smaller dimension we call as the thickness, right? So that's the essential difference, that one distinguishing dimension is there. All three are not of the same order of magnitude. Unlike in the original 3D, which is where your order of magnitude of L is same as order of magnitude of B, which is also the same as the order of magnitude of H. In other words, they are not numerically necessarily equal to each other. It's not like if L is, let's say 5 meters, B is also 5 meters, H is also 5 meters. It could be 3 meters or 2 meters, whatever. But essentially you are having cuboid-like structures or sphere-like structures or ellipsoid-like structures, where you are essentially dealing with things which are not, if you take the ratio, they are not very different from unity. They are close to unity, at least in terms of orders of magnitude. So this symbol of O with brackets next to each other is a symbol that's very commonly used in a lot of fields of mathematics, which just means order of magnitude. So the order of magnitude of B, order of magnitude of L, and order of magnitude of H are all one and the same. That's what we refer to this way. The distinction between plate and the shell, of course, being that the plate has no initial curvature, shell has an initial curvature, but plate can also get into a curvature because of the bending moments that are there, or even torsion for that matter. It can lead to curvatures, and therefore no longer you are having a mid-plane, for example, you will have a mid-surface, and therefore it is called as a shell. So just like beam can be a generalized term for all of these kinds of structural elements, similarly you can say shell is the generic name for this. Plate could become a special case with wherein you have zero initial curvatures, both twisting and bending kind of curvatures, or in all directions it is zero curvature, and then you end up with that. Now there is a possibility in most aerospace structures, like for example I was giving you the example of the let's say a T section or an I section spar, where it can be considered to be made out of two plates. Flange is a plate, the web is a plate, and these two are joined to each other in some way. So I can, instead of having to jump from 3D to 1D, which involves a two-dimensional reduction, which is a fairly complex process because it involves partial differential equations across the cross section, x2 and x3 being the independent variables, I can go from 3D to 2D to get to the flange and this web, and then from 3D I can go to 1D. I can have a two-step dimensional reduction, where at each stage I have only ordinary differential equations to solve. When I go from 3D to 2D, I have to deal with only x3 as the independent variable, the thickness. So I'm essentially shrinking the thickness to 0 and going from a finite thickness plate to a 0 thickness surface, a mid surface or a mid plane. Some reference surface, need not be the middle plane, it could be somewhere else as well. There are sometimes advantages of going for surfaces other than the mid surfaces as well. Then on the other hand, again going from 2D to 1D, so here we already removed x3 dependency. So x3 is removed. Remove the thickness coordinate x3. Here going from 2D to 1D, we are removing the breadth coordinate as well. So in other words, we are removing x2 and we are left with only x1. So a 1D model, everything will be a function only of x1, that is a coordinate along the length of the beam, because no longer we are dealing with the beam as if it was a 3D body, we are just dealing with it as if it was a curve, or in the simplest case just a straight line, and in the undeformed configuration. So then because for a line or a curve you just need one coordinate to say where the point is. That is why it is a 1D model, and that single coordinate, without loss of generality, we can call it x1. So there is whereas when you are going directly from 3D to 1D, which might be necessary in many cases where you do not have a thin kind of a strip, kind of a configuration, in many cases the cross section of the beam may not be an I section or T section, channel section, etc. It could be a rectangular cross section where the breadth and the height are of the same order of magnitude. So something like this. Maybe I don't even need to draw, because that is an example here. Here itself you can see that the thickness divided by width is not so small. It's not like order of magnitude difference. Yes, numerically thickness is smaller compared to the breadth, but if I divide the thickness divided by breadth, it is not very much smaller compared to 1. Similarly, if I divide the breadth by the length, it may not be very small. But still, if I want to model this as a beam, I cannot first of all go to a plate and then to a beam model. I have to directly jump from 3D to 1D, in which case I have to remove, what are the two that I have to remove to get to this? Which two coordinates? Here I had to remove x3 to get there, here I had to remove x2. So obviously here I have to remove. Yes, exactly. So both of them simultaneously. So there I was able to remove one at a time. So it was simpler. So I had ordinary differential equations, or ODEs, at each stage to handle. Now here I will have partial differential equations to handle, but the end result is one and the same. I'm essentially getting to a 1D model which is going to retain only an x1 dependency, no longer an x1, x2, x3 dependency which was there in the 3D model. Okay, so this is essentially the overall process that is of interest to us. But now we come to this 8th assumption, which is the Kirchhoff-Love hypothesis. So let me, maybe I'll just remove this. Here's the entire board. So even before we get there, one more thing you need to be aware of for the plane stress problem is that only sigma I3 for the plane stress assumes sigma I3 equal to 0, even though it's very small compared to sigma alpha beta. It's not exactly 0, we assume it is equal to 0. But that doesn't mean gamma, so in other words, it does not imply gamma I3 equal to 0. In fact, that is a different kind of problem, what we would normally call as a plane strain problem. So this is called as a plane strain problem. We don't encounter too much of this in aerospace, but there are examples like, let's say, a rocket, solid rocket motor casing, especially if it's a long solid rocket motor casing, that typically has a plane strain kind of a thing. It could be a part of a missile or could be a part of a launch vehicle. So essentially an internally pressurized vehicle, but fairly long. A non aerospace engineering example which is very commonly given for this is a dam across a river. So when you have a dam, you are essentially trying to block the water either completely or to reduce the flow, in which case it is typically constrained to not to expand in the direction along the length of the dam. So if this is, let's say, the flow of water and this is in a river and this is the dam that you're talking about, so essentially you're constraining this along the length so that it cannot increase or decrease along the length. So essentially your gamma 33, if that is the direction, so essentially your x3, so you will have that gamma 33 equal to 0. Similarly, your gamma 13 and gamma 23 can also be shown to 0. So this is a different class of problems. Gamma I3 equal to not equal to 0. It's called plane strain as opposed to plane stress. So where this is applicable is when you have very thin structures, and even if, so the case where it is exactly applicable is when you have a thin plate. So if you can draw a cross section of this, it just essentially looks like this. Need not be rectangular or square like what I've shown, but essentially something which is thin. It could be any arbitrary shape as well, but essentially it is like this. And if you have, let's say, stresses like this, which could be either tensile or compressive, it doesn't matter, and it could even include in plane shear stresses, and let's say this is the x1 direction, this is your x2 direction. So essentially this is your sigma 11, this is your sigma 22, and those shear stresses there are tau 12. So when it's very clear that if this is the overall load, then these are the overall stresses, you will anyway not have any of the sigma I3. So this is an example where this plane stress is exactly valid. Okay. So in other words, there is a thin plate and you are loading the plate only within the plane. So for example, it could be this table, we are only trying to pull from either end of the table or this end, or we are trying to shear it in either case. So all these are in plane quantities, in plane normal, in plane normal, in plane shear. So when I have something like that, then this is exactly satisfied, which is why we call this assumption an ad hoc assumption. It is satisfied in some cases like this, but this is a very, very simple case that you may not find very frequently, especially in aerospace engineering structural components. Very rarely is a particular component loaded entirely in this way. There will be other kinds of loadings that are present, but a good approximation for many skin panels is this, and therefore many times you will see that this is kind of used. Similarly, for the web of a spar, let's say an ice spar or T spar even, then you would say that something like this is valid for that structure as a whole. So then you could kind of use it exactly. But in most cases you will have out of plane loading, and that out of plane loading can either be pushing, we already saw the example of all your laptop weights on the table. So similarly, the pressure in the case of let's say the top or the bottom of the panels in the wing. So in all those cases you have a normal stress. There sigma I3 is small but not equal to 0, and therefore it is an approximation, and it is also used in that case also quite extensively, because of the fact that, as I said, that even though that stress is there, that pressure is there, these sigma 11, sigma 22 which are resulting because of that pressure, because that pressure, remember these edges are constrained in some way, because one end could be attached to, let's say, a transverse. So this is the skin, let's say wing skin. Okay, now this could be, so this entire thing could be attached to a rib, which is essentially a transverse stiffener, right? So you could have another rib which is to which the skin is joined over here, that's also a rib. And then you could have at this location, let's say, a spar which is running and spar flange, and this could be a stringer. So in other words, there are certain boundary conditions in the x1, x2 plane for this panel or plate, and that kind of takes care of holding it in place. That's how the panel stays in its place on the overall wing. So when you have a structure like this, the load is typically in terms of pressure load on top of this, and also maybe shear if you have a viscous flow, a low Reynolds number, typically lower speed aircraft or smaller aircraft, you would have that quite dominant. But even when you have pressure which is there in all aircraft, you know that there is going to be a sigma 33 which is equal to that pressure on the top surface. At the bottom surface, whatever it is exposed to inside, maybe it is just empty, and or it is let's say there's a fuel tank there and it's a pressurized fuel, though typically it will be in a bladder. That bladder might be exerting a force underneath the skin if it's a top panel, or if it's a bottom panel from the top, it will be exerting a pressure, both because of the pressure within the fuel bladder as well as the weight in this particular case if it is a bottom skin that we are talking about. In either case, though, that will be of the sigma 33 will be of the order of magnitude of the pressure that is being applied, right? On the other hand, your sigma 11 and sigma 22 will typically be much larger compared to your sigma 33, because there will be an amplifying factor which will be of the order of magnitude of, if I call this as L and B, it will be either L by T or B by T, which will be multiplying your P, and therefore you would have these much larger. I don't know if you remember pressure vessels stresses have you dealt with in deformable bodies, pressure vessels, hoop stress, longitudinal stress. Have you heard of these concepts? So typically if you have a cylindrical pressure vessel, you should have most probably studied this in deformable bodies. So you will see that this, if this thickness is T, this is a circular cylinder of radius R, then you typically, and say inside pressure is P, then you will see that the hoop stress, which is the circumferential stress, that hoop stress, sigma hoop if I call it, or sigma theta, whatever, that will be equal to P R by T, where T is the thickness, R is the radius, and P is the pressure. Already you see this is a thin walled cylinder and fairly large, so your R by T is a very large number, could be of the order of 100 or so. So which means that it's 100 times the pressure. So neglecting something which is just 1 times the pressure compared to 100 times the pressure, or anywhere between 10 to 100 times the pressure, may not be as bad a approximation as it seems upfront. But you will not be able to handle a lot of things that are happening there if you take it exactly as 0. Maybe you can take it as 0, calculate the other things, and go back to the what are known as the 3D stress equilibrium equations in order to get the ones that you had assumed to be 0, namely these sigma I3s, and you can now use the 3D stress equilibrium equations in order to calculate that and find it out that it is after all not 0, but nonetheless it is small compared to sigma alpha beta, which is sigma 11, 22 and 12, right? So similarly, if you are looking at the longitudinal stresses in this, that is your sigma L, not the capital L that we are using with the fiber direction, but a small l, so then it's along the cylinder direction. So that is typically your PR by 2T. It's about half the hoop stress, but still you have an R by T factor. If that is 100, it's 100 by 2, or about approximately 50 times the pressure. So that's also quite large compared to what your sigma 33 will be, which is of just the order of the pressure. It's a boundary condition as far as one of these surfaces is concerned. Okay, so it will vary from whatever is the boundary condition on the top surface, which is exposed to the airflow, to the bottom surface, which is whatever is within the wing. And similarly for the bottom panel of the wing, the bottom surface will be the pressure, which will be fairly large because it has to generate the lift. And then you have whatever is the interior of the wing, that will be causing some weight and or pressure. So that will also be taken into account. But nonetheless, this factor is there of R by T. Of course, there it's not a circular cross section, it is an airfoil cross section. So you will not have simple equations like this with which you can calculate. You might have to do a numerical analysis, typically using computational software like an Abacus or a Nastran or its ANSYS, etc. But at the end of the day, you will find that these are large compared to the stress which is coming purely because of the boundary condition. And of course varying from one boundary to the other, that is along the thickness. It could be varying, right? Even though it's a small thickness, it has to change from whatever is the pressure of the airflow to what is inside, what is contained inside. So whatever is the pressure of that, right? So same thing when you're, instead of a pressure vessel, you're having a panel. So same kind of argument works, that there will be this amplifying factor. So I call this R by T, either here or there, is essentially what we call as an amplifying factor. Your actual applied load is P, but the stress that you're ending up with, the dominant stress, are along sigma 11 and 22. Very interesting. You're applying a pressure which is along the 3 direction, but the result is a sigma 11 or sigma 22, which is so large. Sigma 3 is also there, but very, very small. Whereas you are having R by T, which is a 50 or 100 times the stress in these 2 directions. Okay, so that is the very important point to note, which is kind of non-intuitive, at least to start with, that I'm applying stress load in one direction. Why is it causing stress in the other direction? That's because of the way in which this has been attached. So this is going to bend because it's going to go in. If I'm applying a pressure, this is going to go in, like how this this tends to go in this whiteboard. Similarly, this is going to tend to go in. So in other words, it's going to develop a curvature where there wasn't any curvature, or if there was a curvature, it's changing that curvature. And because it's a shell, typically the bottom surface of an airfoil will be almost flat, whereas the top will be much more curved. So initially it has a curvature, but that curvature also will change slightly with that particular thing, and that change is essentially bringing in bending. So that bending curvature is what is causing all of these issues, right? So bending is something that is going to be common not only with plates and shells like these, like the skin, but also with the spars and stringers, etc. In particular the spars, because the stringer might be just an axial load, just a compression or tension. It could be just a rod or a column. But as we said, we are including all of that in 1D and calling it a beam, a generalized beam, that is, and therefore that will involve as well. So typically you can see there is a parallel between how either of these models are used, whether it's a plate and shell model on the one hand, or the beam or generalized beam model on the other hand. So we will draw out some of those parallels and then introduce the Kirchhoff-Love hypothesis and showcase the equivalent in the case of the beam as well, which is the Euler-Bernoulli. I'm sure you would have heard somewhere, and once we reintroduce that, you will see maybe something clicks in your memory. So you can think of 2 kinds of quantities. One is, or 2 kinds of structures. Let's say we'll have plates or shells on the one hand, and beams, what we also include rods, columns, shafts, etc. on the other hand. Okay, so now essentially this is both are dimensionally reduced models. So that's the commonality between them, is that even though in reality they are 3D structures, we can use for computational efficiency a dimensionally reduced model, not 3D but less than 3D, in this case 2D, and in this case we use a 1D model. And in order to get there, we need to make certain assumptions, like what you were highlighting in yellow earlier this morning. Aryek was talking about, you are looking at certain assumptions which are very critical in going from one step to another. Similarly here also, going from 3D to 2D or 3D to 1D, you need to make certain assumptions, and those assumptions are what are known as, in this case, the Kirchhoff-Love hypothesis, and in this case the Euler-Bernoulli whereby certain assumptions are made in terms of how the deformation takes place, right? So in order to understand that, of course it's named after 4 famous scientists over here. So we'll talk about Euler in fact quite a bit, but all 4 contributions are quite significant, and these kind of help in further simplifying whatever we've been talking about. So the Kirchhoff-Love hypothesis is in terms of your remaining strains. Remember, there were 6 strains, but 3 of them got eliminated because sigma I3 was equal to 0. Okay, so this is not nothing to do with Kirchhoff-Love, but just to recollect what we had, remember, gamma 11 all the way to 2 gamma 12. Now we said that these 3 are not equal to 0 in a plane stress problem, okay, but they can be derived in terms of the other 3. Why? Because remember this equation that we had, we have a matrix which is multiplying your sigma 11, sigma 22, sigma 33, tau 23, tau 31, tau 12, right? Now plane stress says that they are equal to 0, right? And this is of course your compliance matrix, which is your S matrix, Sij, where I and j of course take on values 1 to 6. Okay, so 6 by 6 matrix, of course having many zeros over there, but essentially this. Now if you look at the 3rd, 4th and 5th rows of this particular equation, it's a single matrix equation, but if I write it as a scalar equation, there are 6 equations, right? Each column of this matrix is going to multiply one of the stresses, and they're all going to get added up to give me a gamma 11, similarly a gamma 12, etc., etc., right? Now if you look at, just focus on these 3 equations for gamma 33, gamma 23 and gamma 31, that is the 3rd, 4th and 5th equations. They are going to be in terms of these quantities, and I can actually substitute over there. For that I can solve those equations. If I solve those equations, I can then substitute for gamma 33, gamma 23 and gamma 31 not as zeros but as in terms of gamma 11, gamma 22 and 2 gamma 12. Okay, so that is why you have, even though you have 6 strains, there are only 3 independent strains. The other 3 are obtained by solving these 3 equations. Okay, that's why those matrices that we were having towards the end of before I erased this board, were all, instead of 6 by 6 matrices, became 3 by 3 matrices. Whether you talk of the Q matrix or Q bar matrix, etc., they were all 3 by 3 because we needed only these 3 stresses. The other stresses were 0. We needed only these 3 strains because those are the only independent strains. The other 3 strains are not independent, they are dependent on the other 3 strains. And if I have these 3 strains, the first, second and sixth, then I can get the third, fourth and fifth in this particular column matrix. So in other words, the reason for leaving out the I3s is different in the case of stress and in the case of strain. In the case of stress, I am leaving out because they are negligible, they are small, approximately 0, so I am leaving out. But why am I leaving out these 3? Not because they are small, they could be substantially large, these 3 strains. The reason why I am leaving out is that they are no longer independent strains, they are dependent strains dependent on the other 3 strains. And therefore, we can do all our modeling with just these 3 strains. Okay, so these 3 strains which remain are all, remember, not having 3, they are having only 1s and 2s, and which is why I can call them as gamma, alpha, beta. Once again, our notation Greek subscripts vary only between 1 and 2. So that is now coming to, so this has nothing to do with Kirchhoff-Love. Okay, so this is prior to Kirchhoff-Love, this already happened. Now we are introducing the 8th assumption. So this is entirely from the plane stress. This was the 7th assumption. Okay, so just I am reviewing what we did already. So now coming from the 7th assumption to the 8th assumption, I am making one more simplicity, that I am not yet satisfied saying that I have only from 9 I got to 6 strains and only 3 strains. Even those 3 strains, which are in general arbitrary functions of all my spatial coordinates, and in a dynamics problem it could involve time as well. Let's avoid that complication for now, but it's a function of all 3 because these are 3D strains. Now we are saying that that is, according to not me but Kirchhoff-Love said that, and we will continue to use that. While they can continue to be arbitrary functions of the larger spatial coordinates, namely x1 and x2, we are saying that they cannot have very large variations with respect to the third or smaller coordinate x3. So in other words, we are saying that it's not fully arbitrary in terms of all these 3. It will have one term which we will call as epsilon alpha beta, which is a function only of x1 and x2, not of x3. And then I will have one additional term which will be linear in x3 and which is having a rho alpha beta, which is also a function only of x1 and x2. So this is Kirchhoff-Love hypothesis. It is essentially stating that it's no longer an arbitrary function of x3, it is a linear function of x3, one term which is a constant with respect to x3, the other which is proportional to x3, and therefore together it becomes a general linear function of x3. But we still don't know how it's a function of x1 and x2, that's where the plate modeling comes into picture. Same way in the case of a beam, we will break it up into parts which are only a function of x1 and then which are linear in x1, x2 and x3. So it's a little complex to write that in this particular form, but it's much simpler for the this. But essentially that's what your Euler-Bernoulli hypothesis does for the beam. It's much easier, instead of mathematics, to put that in the form of statements as to what exactly physically is happening when you make the Euler-Bernoulli hypothesis, and then you will see the same thing is happening in a similar fashion with respect to the Kirchhoff-Love hypothesis. So maybe this will help you recollect or jog your memory. Does this click somewhere? Yeah, plane section remains plane. So in other words, you have a beam. Okay, any arbitrary cross section it could be. So if I cut somewhere here, irrespective of what kind of loads I am applying, some distributed loads, whatever, at any place where I cut, that's called a cross section, because you're cutting it across the beam and you're witnessing what is happening at that particular cross section, right? Now we are saying that any cross section of any beam, not we, Euler and Bernoulli said that, If originally, of course, it is plane, when there is no load, that all these loads are not there. This is a concentrated force, this is a concentrated moment, this is a distributed force, may not be constant, it could be varying, whatever, arbitrary. You could have multiple numbers of these. Whatever the loading, Euler and Bernoulli say that a section, if you take, of course, before the application of the load, it was plane. That's how you define a section, in fact. Now, after you apply the load, the beam will deform in some way, but that same cross section which was there will now be somewhere over here, let us say. But earlier it was plane, now also it remains plane. That's what plane section remains plane actually means, right? So in other words, there is no out of plane deformation taking place. So in other words, I'm trying to bend this. When I bend this, there was a cross section before I applied the bending, which was like this. Now, because it is bent into a curve, that cross section has now come here, but it has not gone inward or outward like this. It remains plane. So that's essentially what he's talking about over here, and that leads to a lot of simplifications in the derivations. We will go into the derivations a little later in a later class, but this is essentially what it is. And this has kind of similar implications here. I will come to that. Hold on. We will introduce one more assumption, important assumption, that also is attributed to Euler and Bernoulli. It's also something about remains. Once again, it is about plane section, and it says remains normal to the beam reference line. What does that mean? We'll explain. So we already said, I'm trying to, when no load was applied, there was a plane over here. When I applied the bending curvature, that cross section has become something like this. Now, but still remains plane. The other thing is, because I'm bending this, therefore, if I take what is known as a reference line or a reference curve, which is what I have plotted over here, that is going to become like this. For example, that could be the loci of the centroids of all of the cross sections. So each cross section I find the centroid, I connect all those centroids, the loci of the centroids now becomes what is known as a reference line or a reference curve in the case of a initially curved beam. Similar to what we would have in the plate where we were talking of a mid surface or a mid plane. Similar to that, we are saying, let's say a centroidal axis, but need not be centroidal axis, some axis that we all agree upon. Depending upon what we take, the intermediate steps will change, but the final results will be one and the same. Doesn't matter which point you choose. In many wing analysis problems, you would choose it, nothing to do with structures, you would choose it as the aerodynamic center, because at the aerodynamic center, you know the lift, you know the drag, you know the aerodynamic moment, pitching moment, and how they vary with the angle of attack of the aircraft between the velocity and the zero lift line. So that really helps. So whatever it is, essentially you're saying that not only is that plane section remaining plane, earlier it was perpendicular to the reference line, even after deformation it remains perpendicular to the reference line. So this was 90 degrees, it remains 90 degrees to it. So that's what this means, that a plane section remains normal to the beam reference line or curve. Okay. So there are two very, very important things. In other words, the beam is a 3D body in reality, but like all other bodies, but we are modeling it as a line or a curve, and that line or curve is getting further exaggerated. It is becoming different based on the loads that I apply. When that happens, there are cross sections at each point of that beam. In reality, each one of them is getting a joyride. So as the line, the reference curve gets curved, initially let's say it was straight, it becomes curved. At each point along that there is a cross section, that cross section is getting a joyride along with it. So in other words, it is going along with it, remaining plane, and it is having a rotation which is equal to the rotation of any point of any location along this, whatever the tangent to that, it's continuing to be perpendicular to that. So that's essentially this approximation that was made. There are more refined beam theories. The next step is typically called as the Timoshenko beam theory. All that Timoshenko did is he relaxed this second assumption and said, no, it no longer needs to be normal to this. Yes, it will remain plane, but as it goes, it will take a joyride, it will rotate as much as the reference curve, but over and beyond that, it might have a small additional rotation in either way, what is called as a transverse shear strain. So transverse shear strain is something that we have talked about earlier, remember? So it's the same thing. All that this was trying to do, Euler-Bernoulli, was to set that transverse shear strain to 0, especially the second assumption. This was trying to set what is known as the warping to be 0, because the cross section remaining plane in reality doesn't happen, it actually warps. And warps means it goes in or out of the plane, and also within the plane there is a deformation. This is very well known. It's one example of that is the Poisson's effect. The Poisson's effect, already we know, whenever there's bending or even an axial load for that matter, the other direction is going to have a change in dimension. So essentially there is a warping in plane and there is a warping out of plane. Most people, when they say warping, they'll only be talking about out of plane warping, but here we are talking of warping in a three-dimensional sense, that a plane section no longer remains plane. It can come in or out, as well as within the plane it can extend or contract, and therefore a general deformation can happen, because every material point is kind of free to move, of course subjected to the other material points that it is attached to, but to some extent it will move in different directions, and overall the cross section no longer remains plane, it no longer remains perpendicular, and that is the reality. But this is the simplest model we will have, and throughout the course we will stick to this simple model where we will be talking only of plane section remaining plane, and the plane section remains normal to the reference curve if it was normal to start with. So that's essentially what we have. Why I'm saying is, if it was normal to the reference curve to start with, in many cases we're going to be dealing with, let's say, a swept wing, because once you're going beyond subsonic speeds of wings, you're going to, let's say, close to transonic, as most passenger aircrafts today are, then there will be something called the wave drag, and to reduce the wave drag you will introduce a certain sweep back. A swept back wing is what you have, and in a swept back wing it is many a times more convenient So if this is the, let's say, the fuselage, then you have a wing which is like this, which is half the wing that I've drawn. So essentially you're looking at something like this. So in many a times the aerodynamic center, which is typically at about 25% for the transonic case and about 50% for the supersonic case in terms of how far it is from the leading edge. So let's say for transonic it is 25%, and for supersonic it is 50%, whatever it is, I'm joining all those aerodynamic centers of different cross sections. Now that would be a useful reference line to have, and many cases you want to have the root which is parallel, the way it is attached or fixed to the fuselage, and therefore this will be your x1 and this will be your x2. So you're no longer having an orthogonal coordinate system with which you're so familiar with, right? You typically have dextral triad coordinate systems. This is a case where the most natural coordinate system to have would no longer be orthogonal. In other words, this angle that you have between that is not equal to 90 degrees. In fact, it is greater than 90 degrees that you have. So we can work with such coordinate systems as well. So that's where you would see that the plane section remaining plane and the fact that it remains normal, initially also, even when there is no load applied, it is no longer normal. Okay, it's already at a certain angle, but if you are to use Euler-Bernoulli hypothesis and Euler-Bernoulli beam theory, what is also known as a simple engineering beam theory over here, you would have to say, not say normal, but it maintains, instead of normal, you would say that whatever angle it was at, it remains the same angle. So in other words, here it was 90 degrees, so it remained 90 degrees. Here it could be, let's say, 120 degrees. It will, if there is a 30 degree sweep, let's say, then it's 190 plus 30, 120 degrees. If it was 90 degree, 120 before application of load, it will remain 120 degrees even after the application of load. So that's when you can apply the simplest beam theory that we call as the Euler-Bernoulli beam theory based on the Euler-Bernoulli hypothesis. Now, if you understand this very easily in terms of what we are assuming the cross section to be and do, you can see a very similar parallel exists as far as plates and shells. People usually think, oh, plate and shell theory, very complex, very difficult, not even for undergrad students, not even for master students sometimes. But if you understand that, it's exactly what you're doing over here, and in fact much simpler, because now you're not dealing with cross sections, you're dealing with just a line element, and that line element is normal to the beam reference surface. So this is the beam reference surface, let's say the mid surface, you're talking of a line. Earlier you were talking of a beam, you were talking of a cross section which was a plane, and you were saying how it is moving. Now all I have to do is to talk about this normal line element. I am here going to say that this normal line element will remain straight and it will not change its size, it will not increase or decrease its size, which is exactly what I was saying there, that there is no warping, it's not going out, not coming in, it is not extending in its own plane. Exactly, instead of a plane, cross-sectional plane, here I am talking of a normal line. I am saying anywhere on this entire plate, at each point I will have these normals, and each one of those normals, if I shrink to a point, that's when this 3D body becomes just a 2D surface. It becomes a plane or a mid-plane or a mid-surface or any other reference surface. Now, same thing here. What happened? I was shrinking the cross section to a zero area, making it a point, and the loci of all those points became the beam reference curve. So the equivalent of a beam reference curve is a plate or a shell reference plane or a reference surface. Okay, so here we have a reference plane in the case of the plate or a reference surface. What we had there was a reference curve or a line, right? So what we had here was a reference curve. Here we have a reference plane or surface, right? And there we had a section. Here we have a, corresponding to that, we have a normal, which is essentially a line. Okay, so that is the equivalent of this section. So whatever we said about sections over here, we will tell about the line over here. So we will say that this line for this plate will, even after I bend this plate, I pull this up, you pull it up the other way, and somebody sits on it, and we are bending this whole plate. It's getting curved this way, but all points on this plate, even as it moves like this, there is a reference normal, and that normal will go along with it as it is, unchanged in length, straight. It is not getting curved, it is going along with it straight, it is continuing as it is, and it will, originally it was perpendicular to this mid surface or reference surface. Even after bending, it will remain perpendicular to it, which is exactly what we were saying here, just that the 2D and 1D got interchanged. Here we are talking of a 2D section and a 1D curve. Here we are talking of a 2D plane, reference plane, and a 1D normal line. So it just got interchanged. The larger part is now the reference, and you are having the smaller part as the normal line. Same thing here also. The smaller part is the section, the larger is the normal that you have, okay? Or sorry, reference curve that you have along the length. So is this clear? Is this analogy between the two clear? Yeah. So it's fairly straightforward to see exactly what we are thinking of, all of which is coming from the fact that a plate is a body in which one dimension is small compared to the others. A beam is a body in which one dimension is large compared to the other. Okay. In both cases, there is a distinguishing dimension, either small or large. So that is the only difference, and therefore the development of the theory, the assumptions involved, and the final results also, the entire step-by-step derivation will be almost identical to each other. So it's nothing to be scared or complicated about a plate or a shell. In fact, this is much more simpler to derive because you're going from 3D to 2D, only one dimension of reduction. Whereas here it's much more complex because you're going from 3D to 1D, which is a 2-dimension of reduction, and the rest of the course mostly will be focused on this particular aspect, the beam theory. So once you understand this, this will be child's play for you if you look at it from this big perspective. But if you listen to others and think of, oh, plate or shell theory, a course, let's say a 4,000 or 6,000 level course, then seems like very, very difficult, but it's just a question of jargon, terminology. If you get hold of that, you will see the parallels between these, and both are equally simple to handle, okay? So I think we still have time. Let's get on. So what does this help us? This is the hypothesis. This is the eighth assumption that we had. So where we have said that not only have we reduced the strains from 9 to 6 to 3, but because that's the only number of independent strains, but even those strains, we are taking away the arbitrary dependence on x3 and making it a linear dependence on x3. Now, each of these have certain physical meanings. Your epsilon alpha beta is nothing but the reference surface or middle surface's strain. So this is the strain of any point on the plate. This is the strain of just the points on the mid surface, because if I set x3 equal to 0, I'm taking x3, let's say, from the mid plane of the plate of this table, then you see that when I set x3 equal to 0, I will get to the mid plane, and gamma alpha beta will just become equal to epsilon alpha beta. But if I go slightly above or below the reference surface, then there will be a contribution which is coming from a quantity. You know that strains are non-dimensional, dimensionless quantities, because for example gamma 11 is defined as dou u1 by dou x1. So u also has the dimension of length, meters, x1 also has the dimension of length, meters, and therefore they cancel out and you have a non-dimensional quantity. So just like gamma alpha beta is non-dimensional, epsilon alpha beta is also non-dimensional, just that this is for any point on the entire plate. This is only for those points of the plate, a subset, which are part of the mid surface or the reference surface. Now, if I want for any other point, I have to add something, and that is going to depend on a particular quantity. This product has to be non-dimensional. I know x3 as the dimension of length, or meters is the units, SI unit for it. So this has to have the SI unit of 1 per meter. Or in other words, this is a curvature. So that curvature are 3 in number, rho 11, rho 22, and there's a rho 12 which is equal to rho 21. Of course, there's a little complication related to that. We'll not get into that. But essentially, your 11 and 22 are bending curvatures, and your 12 is the twisting curvature. Either 12 or 21 is essentially your twisting curvature. So what happens when you have a bending curvature is that there is no effect on the mid surface or mid plane as far as its strain is concerned, but any other point above or below is going to be transported because of that curvature by however far it is from that mid surface. In some cases, which is above the mid surface, positive, below the mid surface, negative, and so it's essentially going to get transported proportional to the bending curvatures and the twisting curvatures, depending upon which strain we are interested in, of course. So there are 3 strains, 11, 22, and 12. When you're dealing with 11 and 22, we are essentially dealing with bending curvatures. When we are dealing with 1, 2, we are dealing with a twisting curvature over here. Okay? Yeah, Elish.
So just to reiterate, so what does like the epsilon, like the part mean again?
Yeah. So you can see exactly what epsilon is if you just set x3 equal to 0. If I set x3 equal to 0, what happens? This term drops off, and on this side this becomes 0, right? So what I'm saying is epsilon alpha beta I can define as gamma alpha beta at x1, x2, 0. And what is x1, x2, 0? It is the mid surface. It's your reference surface. So epsilon alpha beta is your in-plane strain at the mid surface. But I can define x3 not necessarily from the mid surface. I can take any other surface also. Then the meaning of the other quantity also will change. Okay? But whatever it is, epsilon alpha beta, if I don't want to say mid surface to make it more general, I would say epsilon alpha beta is the in-plane strains, because it involves three quantities, remember, 1, 1, 2, 2 and 1, 2. So 1, 1 and 2, 2 are in-plane strains. So let's take the table example once again. Let's say you are pulling the table from that end, I'm pulling it from this end. It's essentially getting stretched, right? So the mid surface or the reference surface also gets stretched. So how much is it getting strained is your epsilon alpha beta. Now we not only pull away from each other, but also we try to bend. So let's say you are pulling that way, I'm pulling this way, somebody is coming and sitting on this. So now it's getting curved, right? So now the role of this starts. So that this is also going to contribute over there, but it doesn't contribute to any point on the mid surface or reference surface. It only contributes to those which are away from it as far as strain is concerned. Of course those points move, but just that they are not strained because of this. The strain is coming only because of epsilon alpha beta as far as the mid surface or reference surface is concerned, whereas this is contributing to the strain of all the other points proportional to x3. So let's name them to avoid confusion. So we will call this as the reference surface strains. So that's what your epsilon alpha beta are, and these are your reference surface curvature. Okay, and both of them involve three components to it. One is your epsilon 1, 1, epsilon 2, 2, and your 2 epsilon 1, 2. Now all of them are mid-plane strains. These are mid-plane normal strains. And to, instead of saying mid-plane, I am writing mid-surface to be a little more generic to include shells. And instead of mid, I can again say reference to be more general than having to always take this. Thanks. You can put it on the table. Yeah. So essentially it's the reference surfaces, normal strain, yeah. And this is the reference surface in plane, or in surface rather, shear strain. Okay. Similarly, as far as rho is concerned, also you have three quantities. One is rho 1, 1 and rho 2, 2 on the one hand, and you have 2 rho 1, 2 on the other. So these are the bending curvatures of the reference surface, while this is the twisting curvature of the same reference surface. Okay. Whereas your gamma alpha beta on the left hand side are your 3D strains. All bodies, whether plates or shells or beams or whatever, are all 3D bodies. They should have a 3D strain. That's where it's the source point, it's the starting point. We are just simplifying that. In general, it can be arbitrary function of x3, but Kirchhoff and Love made life simpler for us by saying that it is linear in x3. It involves a term which is constant with respect to x3, depends only on x1, x2, another term which is proportional to x3, and the one which is constant is essentially strains of the mid surface. The one which is proportional to x3 is essentially a contribution of the curvatures, both bending and twisting. Yeah. Okay, let me see. Yeah, we still have time. Yeah. So how does this help us, right? So we already have a term where we had that Q matrix, we had the sigmas, we had a Q bar multiplying the gamma 1 1 2 2 and 2 gamma 1 2. Now I can substitute this over there and I can kind of integrate with respect to x3. Then I can separate out the in-plane behavior and the bending and twisting behavior separately. So which is again, we would be going from a 3 by 3 matrix again back to a 6 by 6 matrix. But the advantage now is that unlike previously where everything was a 3-dimensional function depending on all 3 spatial coordinates, in the so-called ABBD matrix, we will be dealing with only the 2 spatial coordinates x1 and x2. Okay, so it's beyond the scope of this course to derive that. I will just write the final expression for that. So this, even though I'm writing on the right side, this has nothing to do with the beam, but still with the plate. So what we are saying is that you have those n alpha beta, m alpha beta, so this is the end result of that process where we start off with where we left off with a plane stress state. When we said plane stress state, we had got that Q matrix, remember, a Q bar matrix and a Q matrix where we didn't related sigma 1 1, sigma 2 2 and tau 1 2 to you had gamma 1 1, gamma 2 2 and 2 gamma 1 2. In other words, all the in-plane strains, all of which were functions of all 3 spatial coordinates x1, x2, x3, but just a 3 by 3 matrix. Now we end up with a 6 by 6 matrix because each of these alpha beta quantities are 3 in number, remember, 1 1, 2 2 and 1 2. So there will be an n11, I will come to what they mean, n11, n22 and n12. Similarly, you will have a m11, m1, m22 and 2 and m12. Similarly, this we have already seen, your epsilons and rhos. Your epsilons are the mid-plane strains and rhos are the mid-plane curvatures, both bending and twisting. And epsilon alpha beta includes both normal and shear, similarly. So now we are going to have, remember, the left-hand side is a 6 by 1 term because each of these is 3 in number. So here also you have a 6 by 1 and therefore this matrix is 6 by 6 and each of these components are sub-matrices, each of which are 3 by 3. In some form, it is an integration of the Q bar that we were talking about. Remember that in general you're not going to deal with only one ply, you're going to have as many as, let's say, 80 or 100 plies. So we are interested in shrinking the whole thing to a mid surface or a mid plane, not each layer individually, right? The entire plate we want to shrink it to one, but that Q bar, whatever we had, that was valid only for layer by layer each ply. Now we want something which is valid for shrinking the whole thing. That becomes little bigger because instead of a 3 by 3 matrix we now deal with a 6 by 6. But the advantage of this is that this equation is a 2-dimensional equation. Both the left hand side and right hand side are functions only of x1, x2. They are not functions of x3. x3 is kind of contained within it and taken together. So in fact A is kind of an integration over x3 of that q bar matrix that we had by summing over all the layers. Similarly, your B is involving a multiple of that q bar with an x3, and then you are integrating. This involves a multiplication, with x3, and this is B is essentially a coupling between them. And now coming to the new terms that we have introduced here, N's and the M's, these are stress resultants. So these are in-plane forces per unit length, and these are in-plane moments per unit length. So what this means is that, once again, the example of Nilesh pulling on the other side, I'm pulling on this side. We are having a distributed load. So I'm actually applying, let's say, a force of 10 newtons over here. You're applying 10 newtons to balance that. Now that 10 Newton, if I'm applying it uniformly, is getting divided equally along this width. So if, let's say, this is about 20 centimeters, it becomes 10 newtons divided by 20 centimeters. Now that's the distributed load, so with which we are pulling, so that's your N11. Similarly, if two others were pulling on this side, whatever they are pulling with, so that's essentially your N22. And then we are not only interested in that, we are also trying to shear it out. So we're trying to shear it here. So that's your N12. Once again, it's the force divided by length. So all of these are having the SI units of Newton per meter. Whereas this is having the force, this is a moment per unit length, so Newton meter per meter, therefore it becomes just Newton, right? So even though it's a moment per unit length, because moment itself is force times length, per unit length you're talking about, of course you're talking of different lengths, the moment is about a moment arm, whereas this length we are talking about on the edge on which we are applying that per unit length, and therefore this is having it's better to keep it as Newton meter per meter, and this as Newton per meter. Okay, so accordingly, of course, your ABBD all will get populated, but they are related to whatever we had left over at the seventh assumption of plane stress. We had those Q's and Q bars. Remember, they were valid only for each layer separately. Now we have a way of combining everything. In other words, these are going to involve integrations over each layer and summation over the number of layers. If there are, in this case, 1, 2, 3, 4 layers, we will sum over all of those 4 layers, and all of that information will be contained within this. We no longer need to deal with a 3D body, we will deal with a 2D body, which is having a 0 thickness. All of the properties that were there on the finite thickness are now concentrated on the reference surface or the reference plane, and that is essentially what we are dealing with over here. In the case of the beam, what we will do is we will shrink the cross section to a point. Here we are shrinking just the normal to a point. There we will shrink the entire cross section to a point, and we will end up with both left hand side and right hand side functions only of x1. Here both left hand side and right hand side are functions only of, I have demarcated this, only things above and the top right corner are associated with the beam. All of this is about the plate or shell. So both the left and right hand side here are functions of x1 and x2, the in-plane coordinates. In the case of the beam, you would have a corresponding result, which is what most of the course hereafter will be focused on, where we will be talking about both the left hand side and right hand side being functions only of x1, and we would have a similar kind of an integration over the cross section. Here we had an integration over the thickness, there we would have an integration over the cross section. Here it was a one-dimensional integration over x3. There, if I deal with the same thing, I can deal with this as a beam. Along the length it is x1, along the width it is x2, along the thickness it is x3. I'm going to shrink the whole cross section to a point. So in other words, I have to integrate over both x3 as well as x2, and therefore it's a double integral that is involved now in order to shrink a cross section to a point. To shrink a normal to a point, I needed only one integration over x3. Now I need an integration over both x2 and x3, so that I'm left with only x1. The end result of a beam model is the simplest that you can have, but to get there, and to get there appropriately without making wrong assumptions, is very difficult. Here, to get to the plate theory is very easy, because you have to shrink only one dimension, which is x3, which is the normal. You're shrinking to a point. Very easy to show the derivation, which is why I've used this as an example to show you the derivation. But using that becomes a little more complicated compared to the beam theory. But compared to 3D theory, both of these are much, much simpler, and that's why beam or shell theory are much more computationally efficient, wherever applicable, of course, compared to a 3D model that you can have, because most finite element software will give you an option whether to do a 3D modeling or a dimensionally reduced modeling. By dimensionally reduced, I mean either a beam or a shell model, but only, of course, where it is applicable. Like, you can't apply a beam or a shell model where the structure is nowhere like a beam or a shell, right? So if a beam is like a beam or a shell with one dimension which is either dominating or being dominated by the other two dimensions, then you can use these to get to the actual theory. Very simple in the case of plate, to apply a little complex but easier than 3D. In the case of the beam, very difficult to get to the correct beam theory, so we will not bother so much about the actual derivations, etc. We will get to the final result because the derivations are a little more involved. But once we are getting to the final result, we will see that applying it is very easy, child's play, because only x1 is involved. Only one independent variable is involved once we reach the final beam theory. So that's exactly what is kind of the parallel between that, and we already saw in the first few classes in terms of the motivation why we need to deal with beams and shells, because almost every structural component on the aircraft or any flying vehicle for that matter is either a beam or a shell, or sometimes even both. If there is 3 levels of dimensional orders, that thickness is small compared to width, very small, and width is also very small compared to length, like what we were talking about earlier. Instead of going directly from 3D to 1D, I can go from 3D to 2D or to 1D, and then from 2D to 1D is 2 steps. So very few problems will actually be, it will be possible to do that, but there are quite a few in the case of the aerospace structure itself. But almost always you will be able to go either to a 2D model like this or to a 1D model, of which I have not written the final expression. We will see that very soon. But essentially that is the simplified models that we are going to have, and in order to reach there, we had to make certain overly simplifying assumptions that you see over here. Similar thing that we made over here, that the normal remains normal, and it remains of the same size, and it remains straight. It is not curved, that is essentially it's not having any warping. So those assumptions are very similar. One case you are talking about the plane of the cross section about which you are making the assumptions, that's for the beam. In the other case, you are doing the same thing for the normal line, which is where you tend to make the assumptions. But end result, a much, much simplified, computationally efficient problem that you can deal with. Let's go to the next one. So people are not satisfied, having made already 2 wrong assumptions of plane stress and then the Kirchhoff-Love assumption, where you're taking a linear dependence on x3, but then you're trying to get to one more thing. You start assuming the either the displacement field or the stress field. Typically in the case of a plate, you will assume how the displacement varies with respect to x3. In the case of beam, you will assume how the displacement varies with respect to both x2 and x3, that's the cross-sectional variables. So some people will say holier than thou, but we will not make a displacement assumption, but they will, if you look closely, instead of making an assumption on the displacement field, somewhere else they will be making an assumption on the stress field. Both of them are equally having major issues. They will have errors in certain areas more than the other. So typically when you make an assumption in the displacement field, the displacement solutions will be more erroneous. When you make an assumption in the stress field, the stress solutions will be more erroneous, because both of these are unknown quantities. You cannot assume them. You have to determine them. That's your job as when there is a homework, or as an engineer in the aerospace industry, you are actually supposed to find them out. But ending up assuming how they are going to vary with respect to the x3 in the case of the plate, or with respect to both x2 and x3 in the case of a beam, you are doing injustice to the whole problem, and you might end up with erroneous result. By fluke, they do get good results for some cases, but once again it becomes what we called as in the morning session as an ad hoc assumption, and therefore not withstanding these tests that we are talking about these two questions, the answer is either a single or a double no. That's the reason why that's an issue. The last one that typically is made is where certain empirical correction factors are involved. I already told you for the beam, the Euler-Bernoulli beam theory is the simplest beam model where these two assumptions are made. If I want to relax the second assumption and allow for transverse shear strain, I end up with what is known as a Timoshenko beam theory, which is the next best beam theory compared to the Euler-Bernoulli beam theory, but it has a major problem because it makes certain assumptions, because of which you need to end up using what are known as shear correction factors. So shear correction factors, without them, the Timoshenko beam theory will give very erroneous results, and you have to look up a table or do your calculation yourself for different shapes. You will have different shear correction factors. In other words, you are applying the model, you are ending up with a result, you know the result is wrong, so you are multiplying by a factor. So essentially what you are doing is you are tweaking the end result to get to what you actually see, observe. So therefore you will have what is known as empirical correction factors. So all of these four are the danger zones that you will have to be aware of. Unfortunately, based on the syllabus, I have to make these assumptions and deal with the rest of the course, where I may not be explicitly stating this, but it will be kind of built into almost everything that is to be done in the rest of the course. But be aware that there are better ways to do it, and better ways are not necessarily more complex ways. There are simpler ways. We can still do it in simple way without having to make all of these assumptions, and we will be getting much closer to what is observed in reality. If you are to do a test either in the lab or a flight test, you will see much better correlation. If you are to do away with this, leave with just the 6. Already remember how complicated we were before we made the first assumption, and by the time we got to 6, we got very simple model. We just got more greedy in terms of making more assumptions and trying to simplify further and further, and ended up with something which is far away from reality. Yes, it works for some very special cases. We showcase that as the proof, and then we say that is applicable to much broader range of problems, which it is not. Okay, so that is what this whole discussion on the assumptions is. So with this, we will end today's class. If there are any questions, I'll be happy to answer. Yeah.
This is only for the static.
Very good question. So the base model, remember, in either case we are going from 3D to either 2D or 1D. We are dimensionally reducing. For that smaller dimension, dynamics doesn't play a big role. Whereas the dimension which remains, it was originally 3D, we have removed 1D and made it 2D. For those two dimensions, the time dependency will still be large. But for the dimension which we removed, namely the thickness dimension, the time dependency doesn't play a big role even in a dynamics problem. So everything that we have talked about is valid not only for statics but also for dynamics, because we have only talked about the process of going from 3D to 2D, the process of going from 3D to 1D. That process is immune to dynamics. But let me give a catch. If it's a very high frequency dynamics problem, or let's say it's an impact problem, then there are certain dependencies on strain rate, etc. So you need to factor those things in. But a major portion of whatever we have discussed, including the assumptions, will still remain in place, just that we have to bring in the corrections for some of those rate dependencies. Yeah. Okay, thank you.